Good morning everybody and welcome to this tutorial titled Simulation-Based Testing with BeamNG.tech. In this tutorial we'll see the basics of how we can use this simulation for testing self-driving car software. My name is Alessio Gambi. I work at the University of Passau and today I will be your speaker. But this tutorial is a joint work with me and other people, including Pascal Maul and Mark Müller from BeamNG. They will be around today for addressing technical questions on the simulator and how it can be used to achieve effective testing. So simulation-based testing with BeamNG.tech. But what's BeamNG.tech? So BeamNG.tech is a photorealistic, accurate soft body physics engine that can simulate vehicle dynamics and damages in real time. This simulator is developed by a company called BeamNG.GmbH, which is a company based in Germany, but with a team that is scattered around the world, which is also active in the gaming industry. So this BeamNG.tech simulator is a spin-off or shares a lot of the code that runs in the BeamNG.drive game. The simulation is specialized on driving simulations, but in general it is supposed, or it can simulate everything, assuming that you can model them according to their soft body modeling. To give you an idea that how it looks like a simulation in BeamNG.tech. If you see here, the software is simulating the parts of the car, which also lets you create realistic crashes. So all the parts are simulated the in terms of physics, and they can break. So that's how the simulator can achieve very good accuracy and can simulate damages as well. So to give you an understanding of why we are using BeamNG.tech as a simulator for generating tests and simulation-based tests for self-driving cars, let's look around who's using it. So, so far, there are a number of papers published in major software engineering and software testing conferences, including ESEC and ISTA, and several tools that rely on this simulator for search-based testing. To name some, we have Asphalt, Deep Janus, and AC3R. You can look at the paper online. And lately, we have a new another paper called Deep Hyperion, which again uses the simulator to generate tests. Other than that, there are students that are using it. More than 20 students across different universities use that for their thesis, and there's also a couple of advanced seminars that are based on the simulator for teaching how to test self-driving car software. In addition to that, this year at the tool competition here at the SBST Workshop, several people submitted their different tools that are based on BeamNG.tech, and maybe, who knows, after today you will use it as well. So let's move back to the tutorial, starting with the goals. So this is a beginner tutorial. So we are going to cover the basics of the framework and how they can be used to generate simulation-based tests. And we also will exemplify some examples of automated test generator. And the idea is that with this tutorial, we would like to give you to introduce you to the simulator and open your mind about all the possible things that you can do with it. Just to be clear, we are going to show only a fraction of the possibilities that are enabled by the simulator. In general, this simulator is designed to be extensible, and most of its code is open source, and there are plenty of mods that are available around. So wherever you don't find a fit to what you want to do with this simulator, consider that it may be possible to extend it as well. Let's start with the first part, getting started. So the resources of this tutorial are published online at this GitHub repository. So you are going to find their setup instruction, the code examples that I'm going to run here, copy of these slides, and links to additional resources. So the idea was that at the beginning, I thought about this tutorial to be some sort of interactive, live, hands-on style of tutorial, but then I realized that in half an hour and 45 minutes of that are allotted to me for today, the possibility of illustrating many concepts would be simply not feasible. So I decided to change a bit of the style of the tutorial. I will work through some code examples, but for more complex examples, I will show you how to run them and where to look at, and I provide you the code in this GitHub repo. So you are still have the chance to walk through this video again and then run the commands that I'm running here, and and then look at examples and then work with them. If you don't have the copy, the way to get it is to register at this web page, register.BeamNG.tech, and use a valid university email address for the registration. So the simulator, it's free for research purposes. So this is how it looked like, the page. You're gonna fill in the data, and then eventually you are gonna get an email that confirms your registration that has an important attachment, which is a .attach.key registration file. And if you don't provide this key to the simulator will complain and then won't start. So in this tutorial, in particular, we are going to use BeamNG.tech version 0.2130. And on the page to download the simulator, you are going to see other version as well. Please download this exact version. To install the simulator, you don't have to do much more than downloading it, which is a big tarball, and extract it. At that point, assuming that you have space to run it, you can run it. So we are going to refer to BeamNG_home as a variable in this tutorial in terms of so this is where you download the software, and in this tutorial I will use c/BeamNG.tech and the version. So one note here is that officially this simulator can run only on Windows, but you can also try it on Mac using parallels. For example, the videos that you're gonna show today in this presentation are recorded using a MacBook Pro that runs BeamNG inside a virtual machine handled by parallels. We tried different configuration, VirtualBox, and other paravirtualization hypervisors, and the only one that we were able to make it work is with Parallel. Pay attention that Parallels is a shareware. So either you have this installed or a Windows machine you need a Windows machine to run it. As a spoiler alert, Linux support will be available soon, but I cannot give you a date. Maybe my colleague Mark and Pascal have more information, but you have to keep your eye open for possible future development. So to run the simulator, there are different ways. The simplest way is to double click on the exec, and that is located under the bin folder in the BeamNG distribution, and this will start the simulator, and the simulator will not automatically be configured to be used and controlled automatically from outside, for example, using the Python API, but it could be a nice and initial thing to do, so you can browse existing maps or create new content. So for example, here what I'm gonna do is, this is running in my virtual machine inside my Mac. I start the simulator. The simulator it takes some time, it goes up, and then you can browse it. Content, for example, you have a list of scenarios, or you can use the free roam activity to look at the levels and the maps. And all those maps that you see here are already available within the distribution that you download, and more can be downloaded as well. Another way to run the simulator, if you want to script it, is to run it through the PowerShell command line. So here, I don't pretend that you are going to type this command. This is just to illustrate that the exec takes some parameters, for example, the manus console to see the console of the simulator while it's running. And this is, you're going to see later that it's the default behavior when you use the API. And then the important part is that there is this register core module util research GE, which is the core of this, that it's basically the API that will let us connect via Python to the simulator. Here you see that BeamNG user is the work dir, so it must be a directory on your system where BeamNG will store its cache and temporary information and all the files that it needs to be to use for correctly working. As I said before, under this BeamNG underscore user folder, this working dir, you must place these touch keys, which is basically how the simulator verify that you have been registered to the program. Another way for running the simulator, which is what we are gonna do in the remainder of this tutorial, is to use it and start it using a Python API called BeamNG.py. So BeamNG.py is an open source project that is available on GitHub, maintained by Mark and Pascal, and it can be also installed as a library from PyPy. Running the simulator using this BeamNG.py API requires to either set an environmental variable called BeamNG home pointing to the folder where you installed the system, or you have to provide it this the location of the executable and the other parameters when you make the call inside your Python program. And this is what we are gonna do later. Just a disclaimer, I tested those examples using Python version 3.7 and 3.9. Other versions may be supported, probably more recent versions, but I haven't tested that. If you don't specify any BeamNG user parameter, then the simulator will default to your home documents BeamNG.tech user path. And remember, this will work only if there are no special characters or empty spaces in the path of either BeamNG home and BeamNG user. This is a known issue, which is mostly related to Windows, but there is no solution at the moment that I'm aware of. So we say that there is BeamNG.py. So BeamNG.py is available on GitHub, and there is plenty of examples that you can also look to understand and learn how to use the simulator. This is the official library providing a Python interface to this system. And it allows basically to control it, to start it, and to control the vehicles and the various elements inside the simulator. So this is the core module, the central piece of this tutorial, and this is what allows and enables automated generation and execution of tests. To make it work, you need to install it. To install it, it's easy. It's just a matter of calling pip install BeamNG.py and the version. For this tutorial, we are going to use the version 1.19.1. My suggestion, I will not go through the details here. In the distribution in the GitHub, there is description on how to install everything. But what we are going to do now usually is to create a virtual environment, activate it, install all the dependencies, and install the library. At that point, you should be ready to go. So in the videos, you're gonna see me activating these environments and then running the scripts. So to run the simulation, you need one call. So you instantiate the object, you import it from the package BeamNG.py, you need the class BeamNG.py, and you define it to be running on your localhost. You provide a port because this acts as a server to which your Python client is gonna send commands. We specify home and user, BeamNG home and BeamNG user, as you see. For simplicity, I store basically everything under C, so I know there are no spaces and what's not. And for the remainder of the program of this tutorial, we will use exactly this configuration. So once you instantiate this object, BeamNG.py, you have to call open. When you open with the parameter launch equal true, that's the moment where the library spawns a simulator and attached to it. When the job is done, you can close it by calling it BeamNG.close. So this is the basic example. So if you see here, there is a pattern. You open, you do things, and you close. That's why the BeamNG.py also comes as a Python context manager. So if you are not familiar with Python context managers, those are classes that you use by means of the with keyword in Python that ensures that when you call them, they are gonna initialize and release automatically when the flow of the control flow exit the block. So in this case, the example is exactly as before, but there is no explicit call to BeamNG.close because this is inside the Python context manager. So this is handled automatically. And this is how we get things running. So we assume that we downloaded the simulator, we installed the dependency with Python, and then we can run it. Now, in the second part, here I introduce basically the main elements that, in my opinion, in our opinion, form a test. So the pieces that you need to run a test, and then we are gonna see in the last part how to put all together to generate tests automatically. So let's start with a basic introduction and terminology about this part. So simulation-based testing can be used to implement X-in-the-loop testing. So X-in-the-loop testing can be software in the loop, model in the loop, hardware in the loop. There is nothing preventing you to use this setup, this simulator, to test models and hardware. But what we are going to do, and what we do usually, is to use it for testing software. So in this tutorial, we'll focus on software in the loop testing. We are going to test the software controlling the car, but not its deployment inside an hardware component. Nor we are going to test a model of a controller. And why we need simulation-based testing? Because probably you already know about it, that testing those driving controllers, so they are continuous controllers that are, most of them, heavily based on machine learning or AI, and those are notoriously difficult to test by traditional means. There is the fact that they are continuous. It's not just an execution that produce from one input, one output. It's a continuous system, basically. It's a loop. And for those systems, concepts like coverage makes little sense. This is our reference architecture for simulation-based testing. We have a test generator on top. This can be a human writing a test or an algorithm that generates tests automatically, that generates some tests. Tests are passed to a test controller. The test controller is the component that needs to start, set up, and tear down tests. So you can think of test controller like frameworks like PyTest or unit test, and we are going to use mostly unit test here, but a test controller can be any form of a Python script that can interact through the BeamNG API with the underlying simulator. So this controller is the one that does the job. In this case, we assume that BeamNG.tech, the simulator, is a black box. So we don't see it and we refer to it by means of the API that exposes its functionality. So the API hides the underlying simulator. The other two components that are relevant in this architecture are the runtime monitors. So the runtime monitor is this component that observes, collects data from the running simulation, and is the one in charge of basically checking oracles. If something happens, then this component will notify the test controller about a passing or a failing of a test, and then the test controller will stop the test and move on. On the other side, there's a driving agent. Driving agents are basically the test subjects. So they are started or connected to the test controller, and they observe and control the simulation. What does it mean? That they have a way to read the data at runtime from the running simulation, compute the control command that drives the car, and send them back to the simulator to have those cars basically driving around. And those are the components that we are gonna see in a moment. So this is the agenda for this part, is the anatomy of a simulation-based test. There might be different ways of doing that, so don't take this for granted. So we start with a precondition to have a running simulator, then we see how to set up the environment and the initial condition of the test, mainly how to place obstacle, how to configure and set up the oracles and the test subject. And finally, we are gonna look at how we can add some dynamism to our test. Let's start with the precondition. So when it comes to running the simulation, we assume that the simulator is running. Now, there are two main possibilities. Either we restart the simulator, a fresh instance of the simulator for each test, or we try to reuse it. Starting the fresh instance in general prevents or reduces the effects of pollution between states, and in a sense also reduce the flakiness of tests, but it takes more time to execute tests because every time you have to restart the simulation and wait that the simulation load and such. Reusing the simulator instead allows you to save some time, which may be a selling factor when you have to run many tests. In general, in this tutorial, we're gonna see how we use one instance at the simulator at a time, but nothing prevents you, provided that your hardware is capable enough to run multiple concurrent instances, so you can even parallelize the simulations. But we are not gonna see it here today. So to start a fresh instance, this is a unit test class. What you have to do is that in each test you can open and close a new simulation. Okay, here I'm using the Python context manager, so I defined two unit tests, and in the first I open the simulation. This is gonna start the simulator and close it, and then I repeat the second time and then repeat the same for each test. Now we are aware that test framework like PyTest, unit test, XUnit test, and what's not comes with some functionalities like setup and tear down methods. So to achieve the same effect, so to create a fresh instance of the simulator, you can start it during the setup and close it down during the tear down. Also, in this case, the tests are simpler, and what happens is that every time you run a new test, one instance will spin off and then will be closed. To instead having a shared instance, so reusing the simulator across tests, you need a slightly different method. So what you can do is to have a class method that are executed only once for each test, but not for each test method, where you set up the simulator and start it. Now we can call this like the main client of the API. It's the client that invokes the open command with launch equal true. So this will cause the simulator to start and to be stopped after all the unit tests are executed. Now in our test, we are gonna still need to use and access this instance of the simulator. What we can do is to again instantiate this BeamNG class, but instead of calling open launch equal true, we call open launch equal false and deploy false. And why we do so? Because in doing so, the library knows that it needs to connect to a server listening in localhost port 64256 without the need to spawning another process. So this is basically connecting to a running simulation. Now at this point, in order to disconnect, we need to close the socket connection, but not the simulator itself. If we call client.close, client A or client B.close now, we will gonna kill the entire simulator, failing to basically share it across tests. But it's still, what I want you to know is that it's possible. And we are gonna see how we are gonna use this exact setup when we need to, in our example of automated test generators. Because in that case, you need to run many instances of many tests. So it actually really matters to save time during the execution by not restarting the simulation at every test execution. So assuming that a simulation is running, now we have to set up our tests. So one way of doing it is to start from the environment. So BeamNG.tech execute tests as driving scenarios. Driving scenarios takes place in the context of levels. Levels are kind of logical containers or deployment unit, if you want, that contains a terrain, a map, all the props, arts, models, materials, all the data that you may use in the simulator, and they must be manually defined. So the assumption here is that you have levels that are manually defined. In theory, you can also use external software, or you can code something to create terrain files and other and other models completely automatically, but this is not supported by the API. That's the point. So you can have software that does that, but it's not inside BeamNG.tech yet. Although scenarios can and we will be defined programmatically. Okay, so we can take existing maps, and there are 19 at the moment, very well defined. There more can be downloaded, and you can also create your own manually. And then on top of those maps, on top of those levels with maps and all elements that can be used inside the simulation, we are going to create tests. So the level folders are located under BeamNG home levels. And here I just show some of them. And then you can see there are many different configurations. Okay, you have racing tracks, you have plain, flat levels, you have mountains, you have testing rigs, whatever you want, it's there. And then you can use it to run your test, your simulation-based test. So to give you an overview on how they look like, this is basically the levels that you can have. So the existing levels are very well defined, are manually crafted, and then they are rich in the details. So you have rigs, you have racing tracks, you have cities, mountains, many different possibilities. Okay, so if you want to instantiate a test here, you can do it. And how do you do it? Then each of these level comes with a name. And then what you have to do is, after you start BeamNG, you create a scenario. So there is a class scenario in which you give the name of the level that you want to use and the name of the scenario that you want to use. If the scenario is an existing one, it will be loaded. Otherwise, it will be created for you. At that point, you can make the scenario, meaning that the API is gonna create all the necessary files on your system to program the simulator. You load it, and then you start it. And that's the basics of everything. You take a level, and then you load it. And on top of that, we are gonna see how we can instantiate the other elements. One central point is the ability to procedurally generate content. And this is a unique feature of BeamNG.tech, which makes it really powerful, but one of the best choice when it comes to search-based software testing, because it gives the tester the full control of all the elements of the simulations that can be programmed directly in, for example, Python. Okay? This is not the case of other simulators that are limited by the fact of using existing maps only, and without the possibility to automatically, control or generate new content. In this case, we focus on roads. So roads are defined as a sequence of nodes, and nodes are points in three-dimensional space on extended with a width of the road. So a road is a sequence of points. At each point in space, you tell the system how wide is the road, and the system is going to create a road for you. There are other attributes that you can set, including the ID, the material, the lane configuration, and the direction of the road. For example, here in this code snippet, I create a straight road which goes parallel to the x-axis, parallel to the y-axis, and it's straight. So I define 4 nodes, and I give it a name to a new scenario, test scenario. I define a new road that it's made of this road rubber sticky. We will see later what's this. This is the name of a material that exists in the simulator. I extend the nodes with the road, and then I make the scenario. So the scenario is going to look like more or less like this. So this code is available on GitHub under load scenario and roads.py, and the code that visualizes road is under the module visualization.py. So as you can see here, the road is made of 4 nodes. Each node defines the same width, and because the nodes form a straight line, we are going to obtain a straight segment in the simulator. After we define the road and add it to the scenario, we make the scenario, load it into the simulator, and start it. There are other ways of generating roads. For example, systems like Asphalt abstract the roads generation from the pure nodes, sequence of nodes, into sequence of road segments. So one can imagine a road as an object that is defined by segments like go straight for 100 meters, then turn left with a 90-degree turn of a radius 40 and what's not. And by creating a sequence of those segments, then we can generate a road given an initial location and initial direction. This is where the procedural generation comes into place, because from the definition of a segment, we can interpolate the points that form the road and then ensure that different segments are seamless, attached one to another. So here what you see is the resulting road from this definition. There are 4 segments, 2 straights, and 2 turns. And this again is a different way of coding procedural road generation. In the end, what it matters is that you generate these road nodes and give it to the simulator. There are in general many other techniques available implemented by tools like AC3R, DeepJanus, DeepHyperion, and all the tools that have participated to the SBST tool competition this year, because each of them, there are 5 tools, they use very different approaches. I'm not going into the detail of what they do because we are going to discuss it later during the workshop. But you can see that there are very different ways of generating roads. So one last point is about lane markings. So we generate roads in terms of their geometry, but and then we attach to them, we define what material makes them. So materials does not necessarily comes with lane marking. So we know that for testing that computer vision or vision-based driving agents rely on the features of the road. The red, the yellow central line, or the solid white line on the side, or what's not. We need to generate lane markings at themselves in the simulator. Otherwise, if the texture that is associated to the material we use to generate the road does not contain those features, they will just be plain. Okay, so they do not come automatically out of the simulator, those lane markings. We need to make them on ourselves. So one way of doing that, and this is what tools like Asphalt and AC3R do, is to imagine roads as made of layers. The base layer is the concrete. So we can use a material like this road rubber sticky, which is basically asphalt, a concrete layer with no lane marking. What we can do then is to draw on top of this the lines themselves. And how we do that, we reuse this logic of creating roads, but we change the material and the attributes. For example, we can use the line white material to have a solid white line and create using this two lines that are the left and right lane marking. We can also have a double yellow or a yellow as a central separator of the lanes using the same technique. So here it's not shown, but we can also set an attribute that says that those roads are not really drivable by the cars. Are they just supposed to be there to change the visual features of the road? The code that does this is in this trajectory generator.py if you are interested to see how it looks like, but that's exactly what it does. Okay, we generate the base road, white lanes, and yellow lines in the middle. This, of course, is a bit cumbersome because you have to generate 4 roads for each actual road that you want to create, but it may be flexible enough for you to generate roads that have a variable width and a different number of lanes. So if you need to create complex intersections, merge, or forks in the roads, then lane markings are difficult to get. So you have to program them. We are not going to see this though here. And this is how it looked like. So we took our road generated with our segments, and then we added this yellow and white lanes on top of it. The alternative, which is adopted by tools like Deep Janus, Deep Hyperion, and the tool competition pipeline for this year SBST tool competition, is that we can create a texture that indeed embeds the lane marking, and then let the simulator adapt it or to the road geometry. So here I report a picture of a road that is similar to what I just showed you, right? There is a right side, and in the left and right side there are white lanes, and in the middle there is a central separator that is a yellow lane. Now this is a texture. What we can do is we can define a material that uses this texture for rendering, and then create a road that uses this material. This is, for example, what it's inside of this TIG level, and that it's available from the Deep Janus website, from the pre-crime group of the University of Lugano. And once you have done this, the generation of the road is exactly the same, like the basic one, but it will render slightly different. Okay, for example, this is how it will render. So this is a trade-off, because you can see that it's simpler and to generate, because once you have the texture, then you can use it to render the roads, but it's also not that flexible, because the moment that your road has a different size or number of lanes, the texture must be changed and adapted. But just that you know it, that's how you can generate lane marking. There may be other ways, of course. There are, once you load a map, there are additional customization. One that you may care of is the one of the time of the day. So you can use the Python API to tell the simulator it's noon, it's a sunset, it's a dawn, or completely at night. You can even change this while the simulation is running, and this will move the position of the sun, cast different shadows, and have different basically color patterns. Now this is how you can set up the environment, the environment, the roads, and lane markings. Let's move on and see how we can set the initial conditions of our test. This is mainly about placing vehicles and objects or obstacles. So BeamNG.tech allows multiple vehicles and objects to be placed at arbitrary location and rotated in any direction. The difference is that vehicles is a generic term to identify cars and actual vehicles, but also complex objects that are composed of possibly many moving parts, things that can break in pieces, because that's what soft body simulation is about, right? Simulating complex bodies by simulating their parts. And those vehicles have a model. Okay, models are listed under the vehicles folder in the distribution. You can see Autobello, you can see, I don't know, Caravan, and many other things. ATK 800, which is the default one that we use. And that's, you can import them and position them inside your simulator, so you can simulate them. The counterpart are obstacle or objects that are static, things like buildings, concrete barriers, and they can be either modeled in outside programs and imported into the simulator, therefore used also in your test, or they can be procedurally generated. So simple objects like spheres or cubes can be generated directly from the API, as we will see in a moment. So to place vehicles, you need to instantiate the vehicle class, provide a name that is unique in your simulation, and a model. So the model, like ATK hundreds, Autobello, or City Bus, in this case is exactly the model that you see in these folders under the vehicle folder. So in this specific case, we assume to have created a straight line, a straight road, for which we know its coordinate, its geometry, and then we are gonna create a red car, which is the ego car that is oriented following the road on the right lane. And then similarly we add all the other cars. In this case, we add a small Autobello car, which looks like a 500 from Fiat, and a city bus. Okay, and then what we do is simply create an instance of this vehicle object and add it to the scenario with the add vehicle call. So, and this basically will import in the scenario whatever model you want. Pay attention that each model that you import may be a complex object. So a vehicle is made of millions of little atoms that must be simulated by the software. So the more you import, the harder it gets for the simulator to provide you real-time performances. So that's why we limit this to a few instances. So let's see how it looks like when we run it. So I created the virtual environment, and then I run the code, place the code inside the module, place vehicle and obstacle, specifically run the test, place vehicle and object, and the test method, it's called test, place vehicles in front and opposite direction. You find this in the distribution. Okay, when you run it, then that's what you get. So you see that the ego car, this red car, is there. On the black screen, there is you see the console of the simulator saying that the simulator now, the API, is attached to all these vehicles, so you can control them. And then I'm manually driving the car around. Okay, so this is how it looks like. The little spheres that you see on top of those vehicles are debug information. So you can enable some sort of debugging information by drawing lines or showing positions inside the simulator, which is really helpful to understand what's going on in your test. So that's how it worked. So we placed the cars on the ground and everything was fine. Placing vehicles, one should always pay attention to the fact that if you place a vehicle somewhere that it's not on the ground, the vehicle must obey the physics law. So if it's inside the ground, it's gonna be crashed by the fact that there is ground around it. If it's above the ground, like I'm gonna show you in a moment, then the moment that you start the simulator, vehicles will fall from the sky and get smashed on the ground. Okay, because that's the expected behavior, right? If you drop a car from mid-air, it will fall. So here what I've done is exactly create one of these cases where I force the initial position of a vehicle to be above the ground, and that's it's something that we can do as well. And when we run the simulation, you can see something like that. So the simulation is set up, and there we go, pam, this yellow car drop out of nowhere. And this is a situation that in many cases who's is beginning with this type of research on simulation-based testing naturally face. Okay, so if this happens, is because your terrain and your assumption about the terrain in your tests are not matching. Luckily, there is a way to understand what's going on, and the way is to start and load the scenario that you want to load, and pause the simulation pressing J, and opening the word editor pressing F11. What's the word editor? This is a very cool thing of BeamNG.tech, which is somehow missing in many of the competitor simulation, is that you can inspect what's going on in your simulation, and then you have tools like the inspector tool where you just point on an object in your simulation, and then this will tell you all its attributes. You know, for example, I can place the camera in some location and say, okay, what's the altitude of this location? What's the coordinate? And once I've done this, I have a better idea on how to set up my test. So this is just to let you know that this is a possibility. Okay, you can somehow debug and pause your simulations while they are running, and then query the word editor for getting all the information that you need. This is for placing vehicles. For placing objects, we follow a very similar approach, and we can, with the difference that objects may be placed mid-air. So the objects, they have collision maps. So if a car crash into them, as we will see in a moment, they actually damage the car, but the object itself, it's simpler. Okay, so you can place it wherever you want, and they will stay there. Okay, so one can even have, you know, floating barrier or weird things if she or he likes to create very exotic, you know, driving situations, but that's still possible. The choice that you have as tester when it comes to placing objects is either generating them from scratch procedurally, and there are a bunch of classes like procedural bump, procedural sphere, procedural cube that you can use. Here I illustrate a code snippet on the left for a procedural bump, like a speed bump. So it has its own attribute, and once you created this object, you can add it to your simulation by adding to its scenario. So we have add procedural mesh, and then we provide whatever mesh is there. So this works for simple objects. And of course, you can attach material to them. So if you don't attach material to them, they will appear in some, you know, default color. They will be existing. They will be crashing your car if you bump into them. But you can also specify additional material, right? You look up the material inside the distribution. So this folder named art. You select the one that you want, and then you attach it to your object. That's one possibility. The other possibility, which comes handy when you want to work with complex objects, I don't know, a concrete barrier with a specific visual pattern, you know, red and white stripes or something like that, right? Those objects can be imported. What you need is one of these DAE file. This DAE file, I'm not going into the detail, is basically a 3D modeling file. What you do, and what I've done, for example, in this case, is to browse the different levels that exist already in the system, and they come with tons of those models. Choose the one that I liked. So, for example, this concrete road barrier, and then tell my simulation, look, this is what you have to take: create a static object, use this shapefile, and import it. Of course, I had also to specify the initial position and the rotation of those objects, which depends on how they are encoded in this DA file, but that was all of it. So I look around, find what I needed, and imported with a couple of statements. So here I show you how it looks like when you want to place obstacle. Okay, this is some of the code that you find in the distribution. The class is called place vehicle and obstacle. It's the same class that we ran before. So I create this simple straight road, and I use this thick road rubber sticky material which comes with embedded lane marking. So I'm just creating a segment. And then let's see what I'm gonna do is I'm gonna test place obstacles. So I code some coordinates. Because I created the road, I know when it starts, how wide is that, where it ends, its direction, and what's not. And I make use of this to position the ego car at the beginning of the road. Actually, it's inside the road on the right lane. Okay, so I'm translating the position from the central node of the road a bit on the side and in front. And then I say, look, I want a couple of concrete barriers inside my test. So what I've done, I've defined two static objects. They are going to use exactly the same model, but they are going to be positioned in different places and rotated in different ways. So this is the file that I'm going to use, and this is how I can import it. So I create an instance of this static object, which comes with the BeamNG API. I define the position, for example, 20 meters in front of the start of the road on the left side. That I give it a name. I call it barrier, and this is gonna create a barrier on the side of the road. Then I also create another object of the same type. Okay, here of course I can also scale it if I want. I just use scale 1 to keep the original dimension, but I can make it bigger or smaller. Okay, you can imagine that this is just a matter of one parameter. Then I define another object which is a bit farther from the start of the road, but then now is positioned in a different way. It's blocking one part of the one lane of the road. So this is what I've done. I add those elements to the scenario. I spin off my simulator. I load the scenario, start it, and then I can switch the camera, the main camera, on my car to see how it looks like. So once I've executed it, I can drive it, and then you see there are these two concrete barriers. And when I drive it, right, I can even go and crash into them. So that's how, for example, you can create tests for object and collision avoidance. You import models of different type, you place them on the road. You can even generate road, you can use existing road, you can do a mix and match of what you want, and then you can create scenarios where the car can crash into things. If I want instead to have to use simpler objects, I can also have procedurally generated objects. In this case, I generated a bump on the road. So to simulate a speed bump, there we go. I generate a couple of cones and give it a material that looks like these road cones with orange, bright orange and white. You see there in the middle of the road. And I also created a big square, actually a cube, to which I use as a material bricks. So it looks like a wall. Once again, because those are real objects, the car can also crash into that. So that's how I can set up the initial condition. Okay, I place the static objects and the vehicles. Now it's a moment for moving away from the conditions and looking at the oracles. So when it comes to testing continuous controllers, which is different from regular unit testing and testing of regular application, we need to think in terms of positive and negative oracles. So positive oracles are the ones that establish when the test pass. Negative oracles, that are the standard one, decide when it fails. And why it matters? Because the test subject is a continuous controller. We cannot wait the end of the test to decide that the test passed. So this is the usual X unit pattern. If the test complete without triggering any assertion, then the test pass. But here there is no end because it's a continuous controller. So we need to make sure that we can identify also when the test pass. Classical example of positive oracles are target areas. So the car must drive from the initial position to some target area, and if it reaches the target area, the test passes. Conversely, examples of negative oracles are timeouts. Okay, the car did not succeed within some time. The fact that there are crashes and damages to the car, lack of movement, and even unsafe or forbidden areas. For example, the car should drive without exiting its lane. So if it goes out of the lane, it's an area that it's forbidden, and then the oracle will trigger the assertion, and then the test will fail. When it comes to checking oracles, one can have the usual trade-off, either to check them online or offline. So online checking requires the so-called runtime monitors. The offline checking requires to persist the data and then do a trace analysis to decide whether or not the execution was successful. Oracles works on data. Okay, they can be defined on object states, position or rotation. The car should stay in its own lane. Absolute values like simulation time, physical quantities, maximum speed or acceleration, and even other sensors. For example, one may have sensor oracles based on the steering wheel position, the actual gear that it's used, or even annotated images and such. These data that are required to evaluate oracles can be obtained by modeling the simulation using the sensor abstraction. So BeamNG.tech provides you this abstraction of sensors of different types, state, timer, cameras, electric sensor, LiDAR, sonar, ultrasonic, just name one, that you attach to the car. And when the sensor is attached to the car, then it can be read at runtime to collect data or to check properties. And this is what these runtime monitors indeed use. For example, here I have the simplest example, the sensor state. Okay, so sensors are defined under the module BeamNG.sensor, and we import state. Okay, so we have a state sensor, we attach it to the ego vehicle, and then once you start the simulation, after we load the scenario, we can pull the sensors. We pull the sensor, we get the data, and then after that we can read it. Once we have a sensor, then we can define an oracle. For example, we can define a target area oracle, something that it's based on position. In this case, what I've implemented is a simple oracle in which we provide a location and a radius. So this is a kind of a circular area and a state sensor. And this oracle will check whether or not the position of the car is within or not this area. When the position is inside this area, meaning that the distance between the current position of the car and the center of this area is less than the radius that we have, then the sensor is going to trigger. So you reach your destination. That's basically what it does. When we put all together in our test, what we have is we define a sensor, we define the oracle using the sensor, and at runtime, after we start BeamNG, after we load and start the scenario, at every, let's say, monitor cycle, we are going to check whether or not the oracle trigger. We pull the sensor, we pull the data, and after that moment, we have the data locally, and then we can check whether or not the target, for example, the target location is reached. And if it does, then we can exit and conclude that the test was passed. Now, when it comes to gather those data, one may argue whether it's cleaner or better to collect the data into a big loop inside the test execution, or use some sort of background process. Uh, Gathering data directly in the main loop, it's simpler to implement because we have only one thread. There is no complex setup or inter-process communication, while if we want to go for some sort of advanced monitoring thing, then we have the issue that, as illustrated in this sequence diagram, that we have to handle this situation. So we can have the test that start BeamNG, set up the simulation, then start the runtime monitor that again is going to connect also to the same simulation, pull the data, and then notify the test about whether the test pass or fail. The good thing of using a background process is that we can parallelize and then spread the load across different processes. Okay? When it comes also to collect data, we may need to collect a large amount of data that then it must be processed on the critical path. Okay? Imagine that you have everything running inside the main loop, then you get images, point cloud from LiDAR and what's not that you have to analyze, and this may take time and introduce performance overhead, then impact the quality of the simulation, because the simulation is running, you are overloading your machine, and then you may introduce some sort of lags between the observation when you collect them and the reaction or the monitoring of your oracles. To reduce this impact, BeamNG.tech comes with this idea of having synchronous simulations, and then synchronous simulations are basically simulations that execute in steps. You define the steps, which are the granularity of your simulation. For example, 60 steps for each second, corresponding roughly to 60 frames per second. You can have more or less, and then you can tell the simulator, now you progress the simulation for this amount of steps, and then you stop. At this point, the physics, the simulation is frozen. Everything it's there. You can read the data, you can pre-process them, you can process them, you can take your time, and once the output of your monitoring of control is ready, then you can resume the simulation for another loop. And this is basically how you can avoid you can somehow tame or handle these issues of synchronizations. So to have synchronous simulations, you have to set the steps per second, define the simulation as being deterministic, and then you pause it. At this point, if we are gonna run this code, when you pause it, there's nothing you can do. So you see that the timer, the logical time of the simulation is frozen, no control act on the car. So if you try to drive the car, it won't move. And then what you can do, what we usually do is in a main loop, we make the simulation progress, calling the BeamNG.step, providing a number of steps. For example, in this case, if we provide 30 steps, after we define that in each second we have 60 steps, this will correspond of progressing a simulation for half a second. This let you control the frequency of monitoring and frequency of control. And then once you have done this, you can do your work and then resume the simulation. When you are done with the synchronous behavior, you can just call .resume, BeamNG.resume, and then the regular real-time behavior is restored. So now we know how to read data using sensor and define oracles. What about test subjects? So we need to connect to the ego car, instruct about the test goal and what's not. That's what we are gonna discuss now. So the ego car is our test subject. Actually, the logic that controls the ego car is our test subject. And this can take several forms. So the logic that controls the car can be directly running inside the simulator. This is an advanced feature. You can program your car as or driving agent as Lua function that is executed in the context of the simulator or outside it. When you run something outside the simulator, this can be an agent that it runs in the main process. So beside or along with the test case, for example, this is the approach adopted by Deep Janus, Deep Hyperion, the tool competition pipeline, or in a different process. So you can spawn another process or let another process connect to your running simulation and then let it download the data and drive the car. This is what Asphalt does, for example. Now, differently than other simulators, all this communication and between processes and the simulator comes from the must go through this Python API abstraction. So there is no support for ROS or ROS2 or other systems that are commonly used to let driving agents take control over the cars. So the pattern is always the same. It's a controller, so the driving agent is going to connect to the simulator, pull the data, compute the control actions, and then send the control commands back to the simulator. So this is the fundamental difference between test subjects and runtime monitors, is that the test subjects can indeed control the cars, one or more. So each car can be controlled separately. And the control takes the form of the usual steering value, -1, +1, left and right, throttle and brake. To define the test goal, we need to consider the fact that the problem that we want to solve and the test that we want to solve, either this be, keeping the lane, avoid obstacle, avoid pedestrians, recognize traffic signs. This is problem and application specific. So we need to find our own way to instruct our agent about what to do. What the idea is that whatever you do, you try to formulate a task, a driving task that the test subject must, successfully complete. And this can be done explicitly if you know how to do it, or sometimes it can be done also, let's say, implicitly. For example, imagine that you have to test a lane keeping system. One possibility, which is, for example, what it's implemented by the Asphalt tool, is to instruct the test subject about all the entire path that it must be followed on a complex road network. So the Asphalt provides a list of coordinates or driving actions like turn left to the next intersection or something like that, that can be understood in this way, that the car can follow. But other systems like Deep Janus, what they do is that they create tests for which the driving task naturally follow the setup. What I mean is, if you want to have a car that follow the lane, keep the lane, you can create one single road, place the car at the beginning of the road, and let it drive until the end of the road. So there is no need for trajectory planning, for telling the car where it has to go. It just follows the road. So in this sense, we can interpret this as an implicit way of defining the driving task. So let's see how we can use or exemplify these three different ways of including test subjects. The first one is to use the BeamNG driving AI. So BeamNG comes with a smart AI that can drive car. It can keep the lane, it can drive inside the lane, it can avoid to some extent to crash into other cars and such. The API, the BeamNG Pi, exposes some methods to configure this driving agent. So, and they are all prefixed with AI underscore something. So here, what you can do is you take a vehicle, so you create a vehicle, you add it to your to your scenario, and then you say you can set up the mode of this AI. For example, manual assumes that you manually provide the destination or a list of checkpoints that the car should follow. Once you've done this, then the car will automatically drive. It's not that it's disabled, the agent. It's simply manually configured. So you can tell the agent to drive in lane and take and have a maximum speed. So in this snippet here, what I've done is I generated a road. I define a destination point as being the basically last point on the road, and then I added to the scenario a checkpoint. So a checkpoint is a specific point that has an ID that then can be used to instruct the BeamNG driving agent to plan a trajectory to reach it. It's basically the destination. This is similar to what Apollo does, for example, where you tell Apollo, look, this is your map, drive to this destination. And then the AI will compute a trajectory if it's feasible. There are many parameters that can be set, risk factors or aggressivity, max speed, and other. So for this, you can look at the documentation. So, but the idea is that you define a waypoint, a destination, and then you tell the AI, drive this car to that destination. That's one way of doing it. Another way is that you run a code, for example, an actual driving agent that will receive, for example, camera images and other data, and then will compute the control commands. For doing this, what you can do is to run this code within the main process, okay, or the main loop. And this is what Deep Janus and Deep Hyperion tools, for example, do. The upside is that it's simple. You can basically, in the loop where you pull the data and then you post the simulation, you can forward the data to the driving agent that computes the control. But it also requires installing all the driving agent dependencies within the other components. And this may or may not be feasible in some cases, because complex agents, like, for example, the NVIDIA Dave 2 that I took and borrowed from the pre-crime group at the University of Lugano, uses TensorFlow, Keras, OpenCV, and other libraries. And this is not necessarily feasible. Okay, sometimes you may need to resort to a different solution. But assuming that it's possible, that's how it looks like. You can use a camera sensor, and the camera sensor in BeamNG provides you 4 different types of camera. The color one, which is what we are going to use, but you can also have pixel perfect annotation, depth cameras, and instance value that tells you exactly what's inside the image to help you testing different levels of smartness of your AI. It's an AI that can use color image, or you need more segmented applications images or not. Okay, this is something that you can achieve easily by setting the camera sensor in the right way. So let's see how for example Deep Janus does it. So what it does, and the code that show here, it's a simplified version of what's on the website at this address, is it defines an NVIDIA predictor, which is a class that loads a Keras model that was pre-trained on images collected from BeamNG.tech that predict a steering angle from an image. This is the classical setup of a end-to-end steering predictor. Okay, it gets an image from the simulator, it predicts a value of an angle. But because we need to drive the car, we need also to compute its speed. This component, given the steering angle and a limit on minimum and maximum speed, it computes also the throttle command. So basically what it does is, if you need to steer a lot, then you are gonna slow down. That's basically it. Once you have this model, once you have this component available, assuming that you already have a pre-trained model as I do, you can put it into the actual execution. And in the actual execution, what you're gonna do is create your scenarios, defining the road and the initial placement of the car as we have done it before, you load your models that specify the weights of your network, and then inside a big while loop, you pull the data, you get the data, for example, data from the camera, and then you ask this model to make the prediction. And once you have this prediction, you can apply the control command. The control command in BeamNG.py looks like this. You take a reference of a car, for example, self vehicles, and then you call control. Control accepts 3 parameters: throttle, steering, and brake. That's what you're gonna pass it. Once you have applied this, you can resume the execution of the simulation. We are still running into the synchronous mode. Then the control will be applied for the next control cycle, and then you come back after you collect new data, and then you repeat. So to show you how it looks like, and this is a bit speed up the simulation, right? Because imagine that I'm running everything on my MacBook laptop. Okay, so I have TensorFlow, I have BeamNG, I have monitoring, everything there. So I need to kind of speed up. If you're curious to see the code, you can look inside the internal versus internal AI.py, which is a file that is available in the distribution. And then you can look at the external driving AI test. So what I'm gonna run now is exactly this test. The test creates a road. It's not a straight road, it's a curvy road. Then it starts TensorFlow, and then it shows you the camera images that are collected from this camera sensor. So the camera sensor collect the image, pass the image to the deep neural network that create the controls, send back to the network to the car, and then repeats the loop. So if you see here, this goes on and on and on. I just changed the view until you hit this white bubble. This white bubble is a representation of this target area oracle. And because we reached that without going outside the road, the test pass. Okay, you see this okay at the end. If the car were driving outside the road, then we are going to observe a failure instead. So that's how you can drive the car. And this went inside the main loop. The last possibility is to run everything into a separate process, and this is what, for example, the Asphalt tool does. And then the child process or the sub process, what it can do is it can query the scenario, the current scenario that is loaded in the simulator, and query the map and its position using sensors. And based on this and some other parameters, it can also plan the control. And then at this point, we are going to have 2 processes interacting with the same simulation for observing and controlling the car. In this case, with Asphalt, I've also tested a kind of path planner that drives the car using the BeamNG driving agent by computing a trajectory for it. We are going to see the details later, but what you can do is you can tell a car to move by telling where it has to be in which time. So you can say that in 1 second from the beginning of the simulation, the car must be in this location, at 2 seconds in another location, and 3 seconds in another location again. And this AI is gonna basically plan a control that tries to achieve these conditions, try to satisfy this condition of being in an exact place at an exact time by basically tweaking the speed. So you can make the points far away, or you can reduce the time, and this will basically result in the car trying to go fast. So to give you an idea on how you can enable such a thing, what you have to do is you need to have in the main loop a way to start a sub-process, for example, using sub-process popen, and a way to kill the process. Okay, killing the process, here we are actually speaking about OS level processes. You can call, kill or task kill if you are on Windows, and this will, kill the AI. In the process itself, what you can do here is to once again attached to a running simulation using the call BeamNG open launch folds and deploy folds. So the running simulation is there. You don't have to restart it. And then you can define your state, get a reference on the active vehicles that are there and what's not. And then you can get road edges. So provided that you know the ID of a road, you can ask BeamNG, give me the information about its geometry. And then once you have this, you can use a trajectory planner or a path planner to decide how to drive the car. If you don't know the name of the road, you can even ask for all the roads in the map, and then you can look it up somehow there. In this case, the details are not here because they are a bit too complex to fit in one slide. But what you can do is you can compute a driving path and then the so-called AI script. So the AI script, as we will see later, is this trajectory. Once you have this trajectory, a list of points that must be reached in time, you can pass it to the AI, the BeamNG AI, using the usual self-vehicle.ai set something. But this time, if you look at, I'm disabling the AI, and then I'm controlling it using the script. So I invoke set script, and this will basically force the car to drive according to this trajectory that I've just computed. So that's how I can configure the test subject. The last piece for this part is adding some spice, adding some additional dynamism. Okay, for example, random traffic and controlling non-playing character cars. So here I'm not going to show the traffic API. You can read about that on the website because I consider that to be an advanced feature, so will not necessarily fit this basic tutorial. So the way to control this NPC vehicle is either by using a checkpoint or by generating a trajectory, one of those scripts. So for the checkpoint is exactly what we have decided before. You tell the car, drive to this location with this maximum speed, and the car will drive itself. Okay, so you can use this to create and make the other cars move on themselves. The other possibility, or a second possibility, is to generate this script where that creates a trajectory implicitly by specifying a sequence of nodes that must be reached in time, as I told you. So here, for example, I exemplify this, saying that at time 0, when the simulation starts, the car must be in the initial position in this leftmost node. Then after 1 second, it must reach this other node. After 2.5 seconds, the next node, and so forth. And because the nodes are displaced, the car will turn left and right. So this is how it looks like. So you have a trajectory that it's made of nodes. Nodes are basically dictionaries that contains X, Y, and Z that tells you where the car must be, and a T. T is the time since the beginning of the simulation in logical time, not in real time. And in this case, what I've done was to define an internode distance of 20 meters and then have a loop that basically place one point, one of these nodes, every 20 meters on a straight line, and tell that the car must reach the nodes in 2.5 seconds. So between the two consecutive nodes, the car in the time between the car passing in two consecutive nodes must be 2.5 seconds. And because I don't change this is basically driving straight somehow at constant speed. But this is a very basic situation. Then what we need is to create a vehicle, add the vehicle to the scenario, and then set up the vehicle AI with the set script. Tests can be created manually, of course, but then we can also use these pieces to create tests automatically. In this tutorial, I'm looking at the two main forms of test generations that I'm aware of when it comes to simulation-based testing, which are parameter exploration. We define one abstract scenario and then we instantiate this by giving value to parameters and generate many concrete scenarios. The other form of automated test generation in this context is the one that rely on procedural content generation, where we can generate many abstract scenarios and either one or more concrete instantiation of those scenarios. So here what I will show you is two setups. One is about testing the car following behavior, which is an experiment based on parameter exploration that is inspired by the Euro and NCAP testing protocols. Basically, there is one car in front, the ego car behind, and the ego car should follow the car in front without crashing into it. And the other one is testing lane keeping, which is a more standard type of test. So we generate roads and then we check whether the car can drive over on those roads without going outside the lane. And this is inspired by Asphalt and many other tools, included the tool competition of this year. So the first case, which you can find implemented into this automation example 1.py, is following a drunk driver. So the idea is that we start configuring the hidden car that the ego car should follow to follow a straight trajectory on a straight road, driving at constant speed. And then we start mutating this trajectory by changing the lateral displacement of these nodes that form a trajectory and the time between the nodes to create some sort of wiggling or let's say weird driving behavior, as you may expect from a drunk driver. So we can increase the speed, decrease the speed, keep the speed at the same time, and turn left and right. For the fun of it, I'm gonna implement and show. I implemented a basic evolutionary algorithm 1+1. There's gonna be only mutation. The population size is 1, and what we do is at every time, at every execution, we mutate this in the individual, we execute it, and we compare with the previous individual, and then we keep the best of the two, and then we repeat. So let's see how it works. So this file is already available on GitHub under automation example 1.py. So because I'm expecting to run many tests, I'm gonna create one shared BeamNG simulation into the main file before invoking the main method. And then inside the main method, what we are gonna do is we create an initial individual. In this case, I'm not gonna create a random individual. I always create this straight line made of nodes that are equidistant, meaning that the car will travel more or less at a constant speed. And how I do it, I know that the road is a straight road, and I'm gonna use this little code to place nodes in a line. Then I define a generic execute experiment that takes one of these individual, meaning this trajectory, create some debugging information to visualize them by creating some spheres. And then what I do, I place the ego vehicle at the beginning of the road. I place the heading vehicle 20 meters in front of it, and then I define a destination point. So sorry that the video is quite fast, but I have to be on time. And then I define the heading vehicle to follow this trajectory that we are creating, and the ego vehicle behind it to reach the goal waypoint at a given speed. And then at this time, what I do, I assume that the execution should stop within some timeout, and I step through the execution, collect the data, and then collect fitness function. In this case, the fitness function is going to be the distance between the two cars that must be minimized. To mutate The system, the trajectory, I have immutator operators that either move the point on the side or change the interarrival time, so we can control the speed of the aiding vehicle. And the loop of the main loop of the generation is that we create a new individual, we execute it, and then we check whether or not the new individual is better than the previous one. And then we repeat either until the budget of execution is exhausted, or whether we cause a crash. And if we cause the crash and the distance is basically less than 0, we have a crash oracle that tells us we stop the search because we already found the best one optimal solution, right? So how does it look like for real? So we can run the script automation example 1. I'm not going to use unit test or PyTest. Everything now it's in a basic script. We are going to see that, and then once again, this simulation is sped up to avoid spending too much time looking at and loading screens. We generate the first individual, and then you see that the yellow car, which is in front of us, is simply going straight until it reaches the end, and then we start mutating it. For example, the first mutation in this case was to move the one node on the side, and it's not a big mutation, but you see that the yellow car is kind of moving left and right already. The speed is basically the same because we haven't changed the interarrival, the time between the points, right? Now I mutate another point, and then we see once again that the car in front are slightly changing its behavior, turning left and right, as we can expect. Those are minor differences, but then sometimes we have better mutations for which not only we change the car that is now driving left and right, but we also drastically reduce its speed. So it passed from 28 km per hour to 16 at some point, and then you see that the ego car is getting closer and closer to it, and then this improved the fitness, and then at this point, bam, the car crashed into it. So we've managed to find a way to crash this car by modifying the trajectory of the aiding vehicle. So this was a first example. The second example, that it's much more close to what we will discuss today in the workshop, is about procedural road generation. So the idea here is to implement a simple genetic algorithm, so nothing fancy, tournament selection and mutation only, no crossover, by generating roads as sequence of segments. So a chromosome is a sequence of segments. The size of the chromosome is fixed to a configurable number, let's say 5, and each part of the chromosome is a different segment and defines a road. By changing, replacing, or mutating those segments, then we can evolve the roads. There are many other ways of doing that, of course. This is just illustrative. And the code, you find it in automation example _2. So let's look briefly at the code. So as before, we are going to run plenty of simulations, so we are going to use a shared BeamNG. Everything is implemented in main. We have a couple of parameters, for example, number of iteration and size of the population. And the population, each individual is a road. And each road is made of n segments. In this case, I say 10, I guess. We are not validating the inputs here. What we do is we execute whatever we have, then we take the best individual, check whether or not any of this execution failed, because if it fails, in this case, the search is over. Then we implement a basic tournament selection, and having selected the individuals, we try to mutate them. Now, to generate random roads, what we do is we have a number of segments and then we append random segments one after the other. So with some arbitrary probability, we can generate the straight segments of a given length, or turn segments. So it can be positive angle or negative angles to have left and right turns. And for simplicity, we cap the radius and the angles that we can generate. So that's how we generate random roads. To execute them, now what we do is we generate a scenario with a different name. We make the simplifying assumption that all of those roads starts from the same point with the same initial direction with a first straight segment. So we ensure that whenever we place the ego car, we can place the ego car basically in the same position, and it will always be on the road. Okay, so this is a bit limiting, but simplifies a lot this example. Then we generate the roads, the road nodes from this list of segments. And once we have the roads, we add the new road to the scenario. In this case, once we can also visualize it with available code, we are not going to do it. We add the ego car, position it in the right way, define a state sensor because we need its position to understand whether or not the car is inside or outside the road, define a target position based on the actual shape of the road that we generate, and then we repeat our usual loop. Okay, so we get the road edges, we define where is the left lane and right lane, and based on this we then can create one of these simple OBE oracle. OBE stands per out of bound episodes, and that this is basically what tells us whether the car is inside or outside the road. Then we configure the AI. In this case we use BeamNG AI to make it simple. We have some aggression factor high to make it drive faster. And what's that? Then we compute the fitness function as the distance between the center of the right lane to the position of the car. So if the car is going too far away from the center of the lane, then we are happy our tests are effective up to the point that the car goes out of the road. And then this is once again what is done in asphalt. For mutation, we either replace a segment or mutate one of its parameters. Okay, and then we repeat this for a number of generation. Then what we have at the end is our supposedly best individual. Of course, unless the car goes out of the road before exhausting the budget, meaning that we found a misbehavior of the AI. So let's see how this looks in practice, and then we are gonna close this tutorial for today. So we activate our environment, then we execute our script. So here we are using 3.9, example number 2. Once again, this is sped up to fit with time constraints of this video. So what's gonna happen here is that we are gonna see different small scenarios. I think this is not generated with 10 segments, but only with 4 or 5. That reddish column is basically the checkpoint, the target that is aimed, that the AI is aiming to find. And then you see here that the roads are different, right? So they are randomly generated. That's why the car also has a different behavior. So this is very curvy, so the car has a small, it drives slowly compared to having straight segments. So the size of the road is variable because we fixed the number of segments. We didn't fix the length of the road. Now, after a first generation pass, we have four tests that were executed, and then we have one that it's better than the other. We do our mutation and selection, and then the generation continue. Okay, once again, what we obtain here is that all the average fitness improved, but not the best individual. Now, to make things more spicy, more interesting, we are gonna uh, set the aggression factor of this car to be 2. 2, it's kind of above the minimum value. It's quite aggressive, so we will see that the car is gonna cut a bit more the lanes, and it will be also faster. Okay, and this is again to show the difference in the fitness values that we can achieve with this test subject. So as you see here, it's still a small number of sectors, short roads. And this is again one parameter of this little algorithm that we can change by simply changing the number of segments that comprise the chromosome. The issue here is that the longer is the road, that easier is to create an invalid individual. And for the sake of this experiment here, this example, I did not implement any validation. So having long road may end up in creating weirdly looking roads. So you see that now, in general, these individuals, all of them have higher fitness function. So here, just to show you that we can change the number of segments and obtaining longer roads, I'm gonna switch between replace this 5 with a 10, and then see that this genetic algorithm can create longer roads. Okay, so this is how it looks like. So, and again, this is sped up. You see how long is this road compared to the other one, right? It's double. And this is basically it for this example and this tutorial. So before concluding, what I show you is I explain you to how to get a grip on this framework. What are the main parts and components that you can use to create your test, and I also give you a short demo on how you can create tests automatically. So if you want to find more, you find and discuss about this, you can follow us. You can check out these resources. We have the SBST workshop, documentation from BeamNG, the tutorial, this tutorial here in bold, the pipeline competition, and many other tools out of there. So with this, I thank you once again. So my name is Alessio Gambi, and with Pascal Maul and Mark Mueller, today we have presented to you this tutorial on simulation-based testing with BeamNG.tech. Feel free to ask questions now.